Welcome back to B110. Today we're going to talk about the stress tensor, which is arguably the most important physical quantity in continuum mechanics, and one that can be a difficult one to understand at first. The stress is a tensor, and we've learned about tensors. Tensors are physical quantities whose components can be represented in a 3x3 matrix. And so we'll see what the stress tensor looks like, and we'll start to understand some of its properties. The most important property of the stress tensor is that it represents the surface forces of interaction within a body. So if you think about a material continuum and you want to expose those surface forces, then you have to make a cut. If we make a cut and remove or isolate a region from a body, then we expose the surface of interaction, and the forces acting on that surface due to the surrounding material are the forces that we're interested in. So because of this, stress has units of force per unit area, and being a tensor, a rank 2 tensor, it's defined by two vectors. One of them is that force per unit area vector, or traction vector, and the other is the unit normal vector to the surface that defines the orientation of the surface at that point. So stress is therefore defined by surface forces, which are forces of action across a surface, in contrast to body forces, which act at a distance and are expressed usually as force per unit mass. So a well-known example of the body force is the weight or inertial force of a body, but there could be other body forces such as those due, for example, to a magnetic field. So the way to analyze and expose these surface forces of interaction within a three-dimensional body is by taking a free body diagram of part of that three-dimensional continuum. Imagine that there are forces acting within a continuous body B, and then we'll take a region R inside B that has a surface S. So here in our diagram, we have our region R within the body with surface S and a point P on the surface with outward normal N, area in its immediate vicinity of delta S, and a traction vector acting on it, T superscript N. So P is the point on S, N is the outward normal to S at P, delta S is the element of surface area surrounding P, and then on delta S, the material in B outside the region R exerts a surface force of delta P on that region delta S surrounding P. So delta P defines the traction vector T superscript N by T superscript N multiplied by delta S. T is the surface traction vector with units force per unit area at point P, and the finite limit as delta S tends to 0 of delta P over delta S. So at every point on the surface we can define this traction vector field. Now, notice in general that Tn does not typically coincide with N, except in some special cases such as when the stress is a pressure field, in which case all attractions would be normal to the surface. But normally they're not. Normally a component of the tractions is also tangent to the surface. So t and n don't coincide. There's components of t that are parallel to n, and there are components of t that are normal to n. So now let's consider the components of the stress tensor, which we now see as defined by two vectors: the traction vector, which has units of force per unit area, and the unit normal vector, which is dimensionless, but defines the orientation of a surface. So if we have unit base vectors, E1, E2, and E3, and we use them to define the outward normals, then they would define three mutually perpendicular surfaces, which are the three mutually perpendicular coordinate planes: the x1, x2 plane, the x2, x3 plane, the x1, x3 plane. Now we can define the traction vector T1 as the traction acting on the face normal to E1. In other words, the traction acting on the YZ or X1, X2, X3 plane. And similarly, we can define T2 as the traction vector acting on the plane whose normal is E2, and T3 as the traction vector acting on the plane whose normal is T3. Now, if we resolve each of these three traction vectors into their three components with respect to that same coordinate system, then we get 9 numbers, the three components of each of these three traction vectors. In other words, T sub I would equal Tij Ej, where Tij is the jth component of the traction vector acting on the ith face, on the face normal to E sub I. So here's what this would look like. Here are the three planes. This is the plane whose outward normal is E1. This is the plane whose outward normal is E2. And this is the plane whose outward normal is E3. Then there are traction vectors, T1, T2, and T3 acting on these three surfaces. And when we resolve them into their components, you see there are tangent components and normal components on the surface for each of those three traction vectors, giving a total of 9 quantities, which are the 9 components of the Cauchy stress tensor. You can see that in each case, the component pointing outward normal to the surface is the diagonal component. So T11 is the component of the traction acting on the face normal to E1 that is also normal to E1. Then T12 and T13 are the two in-plane or shear components of the stress in that plane. Similarly, T22 is normal to the plane, the E2 plane, acting in the direction E2. And the shear components are T21 and T23. And similarly, T33 is the normal component, T31 and T32 are the shear components. Now, I've drawn these arrows in the positive directions, namely in the same directions as the base vectors, and on the positive faces, namely on the faces whose outward normal are the unit vectors. So these are all positive components of stress as they're drawn. So we'll emphasize that again in a moment. Now let's go back to our expression where we defined these stress components in this way, and take the dot product of it with Ek. So now we get Ti dot Ek equals Tij Ej dot Ek. And then Ej dot Ek would be delta Jk, 1 when j equals k and 0 otherwise. So that would turn the j into a k, which would therefore be Tik, which says that we can write Tij as equal to Ti dot Ej. So these are just equivalent definitions of the components of the stress tensor in Cartesian coordinates. So Tij are the components of the rank 2 stress tensor defined by T, equals Tij Ei dyadic Ej. Note that the notation sigma ij is frequently used for the stress tensor as well, and sometimes tau ij. So the diagonal components of the stress tensor which are T11, T22, and T33, are the normal or direct stresses. The off-diagonals, T12, T21, T13, T31, T23, and T32, are the shear stresses. Now let's think about our cube again. If there were equal and opposite components of traction applied to the opposite faces of this, then you can see that they would all balance, all the forces and moments would balance, and this cube would be in equilibrium. Now, all of those tractions would be pointing in the opposite direction if they were equal and opposite. And so all those positive tractions would be negative on the back sides of this cube. But all the faces that they're acting on would also be negative. So therefore, as drawn, all the stress components would again be positive if we had the same view on the back side of this cube. So what that means is, regardless of whether you take the positive side or the negative side of the cube, if the normal stresses are directed outwards, then they're positive. If they're negative, then they'll be directed inwards. The same goes for the shearing tractions. The positive shearing tractions are the ones that are going to deform the surfaces of the cube in such a way as to make the coordinate angles more acute, and the negative tractions would tend to act in the opposite directions to make the coordinate axes more obtuse. But it's the sign of the normal stresses that's of particular importance and interest. So because positive normal stresses act outwards, they're referred to as tensile stresses. So when T11, T22, or T33 are greater than 0, we call these components tensile stresses. And when T11 or T22 or T33 is less than 0, we call those components compressive stresses, components that press in on the region. So we'll finish now with a couple of simple examples. So the simplest stress field we could imagine is this uniaxial tensile stress field. So imagine we have a uniform cylinder with cross-sectional area A and forces acting outwards at the ends, F, in the x direction. Then sigma xx would be the magnitude of F divided by A, and the stress tensor T would be sigma xx 0, 0, 0, 0, 0, 0, 0. That's the only non-zero component of the stress in this simple uniaxial condition is sigma xx. And it's positive because it's an outward tensile stress. Okay, so here's another example where now we have a slab with dimensions L in the x direction, W in the z direction, and H in the y direction. Forces of magnitude F pushing inwards in the x direction, and shear forces of magnitude P acting on the z faces in the negative x direction on the positive y face, and in the positive x direction on the negative y face. So this then gives us that sigma xx equals minus f over the area of the face normal to x, which is w times h. Sigma xz equals minus p over L times h. And therefore the components of the stress tensor will be sigma xx, 0, sigma zx, 0, 0, 0. And then we'll see that the stress tensor is actually symmetric, so sigma zx will also be in the 3, 1 position. So here's another example of normal tractions applied to the cube with areas A1, A2, and A3, normal to x1, x2, and x3, and forces F1, F2, and F3 acting on each face. Notice I've drawn F1 as being tensile, F2 as being tensile and somewhat larger, and F3 as being a compressive traction. So sigma xx would be F1 over A1, sigma yy would be negative F3 over A3, and sigma zz would equal F2 over A2. In this case, where all attractions are normal, the stress tensor is diagonal. Since all the off-diagonals are 0, that means that sigma xx, sigma yy, and sigma cz in this example must be principal stresses, and x, y, and z must be principal axes. And by convention, we would denote sigma zc as T3, the third principal stress, sigma xx as T2, the second principal stress, and sigma yy as T1, the first principal stress, such that T1 is greater than T2 is greater than T3. A simple example that we've mentioned before in class is a hydrostatic pressure stress case. So imagine this is a sphere with pressure acting in on all directions, P. This P is a negative stress. It's normal to the surface everywhere. And so the components of this hydrostatic stress case are just minus P, minus P, minus P on the diagonals. So these are not only principal stresses, but this is also a deviatoric stress tensor because its trace is 0, and it's an isotropic stress tensor because it's the same in every frame of reference. In this example, let's imagine we have a unit cube with lengths 1 in each direction and shear tractions F acting on the y face in the x direction and on the x face in the y direction. So these define shear stresses tau xy and tau yx. And you can imagine that to be in equilibrium, there must be equal and opposite shear tractions acting on the opposite faces. So the stress tensor here has no normal stresses and only shear stresses tau. A more general special case of stress is called plane stress. In plane stress, all of the stress components are limited to a two-dimensional plane. None of the components in the third direction are non-zero. So in this case, let's draw plane stress in the xy plane. This entire body is in a state of plane stress, and now we'll draw a region within it where in general we will have normal stresses in the x direction, sigma xx, Normal stresses in the y direction, sigma yy, shown here as tensile. And shear stresses in the xy plane. So in other words, acting on the x surface in the y direction and acting on the y surface in the x direction. But no tractions with components in the z direction. In other words, no stresses with a z in them. And no stresses acting on the z equals normal face. So the state of plane stress is T equals sigma xx, tau xy, 0, tau yx, sigma yy, 0, 0, 0, 0. We'll talk more about the stress in class.